Hi everyone. In our previous lecture, we introduced Newton's laws and described how those laws informed the results of motion due to forces. They were a description of how objects react to forces acting upon them. We talked about what forces were. We described some different forces, or I should say we identified some different forces. In this lecture, we're going to work with Newton's second law and Newton's third law to talk about how we can solve problems in terms of forces and the acceleration of objects. So we'll start with a reminder of what Newton's second law is. Remember, Newton's second law tells us that when a force acts on an object, the acceleration that the object experiences is proportional to the mass, or rather that the acceleration is equal to the net force divided by the mass. The idea of what a net force is one of the first things that we're going to work with today in the next example problem that we do. I'll remind us that we got the units for force by considering the rearrangement F equals ma. Mass is in units of kilograms, acceleration is in units of meters per second squared, and a kilogram meters per second squared is what we call a Newton, and that is our unit for force. So we will see that all of the forces that we're given, or the forces that we solve for, are given in units of newtons. Let's consider this example problem here, where we have two forces acting on an individual object. So we have this large black circle. Forces F1 and F2 are acting on that as shown. We see that F1 is smaller than F2, so the arrow is drawn to be a bit smaller. And we see that they are acting in two different directions. F1 is down in the fourth quadrant, F2 is up in the first quadrant. If we want to find the net force is the vector sum. So we could write here F net is the vector sum of the first force vector plus the second force vector. And we remember from adding vectors, this means that the x component of the net vector is f1x plus f2x, and similarly the net component, the y component of the net vector would be f1y plus f2y. So our job is to decompose these vectors into pieces, right? So I've got f2x right there, and I've got f2y with that vector on top. Similarly, for f1, we could use a different color here, and we could say we have f1x and f1y, like so. So our job is going to be to find what those x and y components are, and then to sum those components to get the net vector. Let's look at F1 in detail, and then I'll just give the results for F2. You can calculate it yourself. So if we have F1 x, that should be the magnitude of F1 times the cosine of theta. F1 is going to have a theta that goes all the way around. So I have 360 minus 20 is 340. So I would have F1 is a 5 Newton magnitude times the cosine of 340 degrees. When I calculate that out, I get 5 times cosine of 340. Make sure your calculator is in degree mode. And I get 4.698, 4.70 if we round to two decimal places. So that's the x component of F1. Similarly, F2, just want to make sure I'm all the way on the screen. Yep. Or sorry, F1y, pardon me, would be the magnitude of F1 times the sine of that angle. So I'd get a 5 Newton magnitude times the sine of 340 degrees. And when I do that, I get a small negative 1.71. Remember, the value in expressing your angle all the way around from 0 and the positive x-axis, that negative value spits out right away due to sine for an angle larger than 270, or excuse me, larger than 180, always giving us negative values, so that would be the third and fourth quadrants. Similarly, we can find the values for f2x and f2y. I'm going to calculate them quickly and then throw them up here. You can pause the video and calculate them yourself and see if you get the same value. So calculating f2x and f2y, I get 4 newtons and 6.93 newtons. Now, of course, the x component of the net vector is just the sum of f1x plus f2x. The y component of the net vector is the sum of f1y and f2y. So I need to go to another page. I'm going to pause again to scribble these values down. Okay, so if we were to then look at the sum of these two vectors, let's add a page here. Our x component of our net vector, right, would be f1x plus f2x. That would be 4.70 plus 4.00 for f1x and f2x respectively. That would have an x component of our net vector, then 8.7. All we're doing is summing the two force vectors, just like any vectors. The net component is going to have a y component. The net vector is going to have a y component. f1y plus f2y would be minus 1.71. We have to keep that negative sign, plus 6.93. And that gives us a value of positive 5.22 newtons. So if we were to draw our net vector, here is that object that has f1 like this and f2 up at an angle, something like that. Our net vector would have an x component that is 8.70, so that's going to have a large x component here. That's f net x, and then a y component that's not quite as large. And if we were to resolve those vector components into a vector, then we'd have some large net vector, maybe something like that. So here in the thick vector that I've drawn here, somewhat sloppily, but I think you get the idea, that's f net. We can find the magnitude of f net by doing the Pythagorean Theorem, right? We have f net x plus f net y. Each of those is squared. So I would have the square root of 8.7 squared plus 5.22 squared. And when I do that, I get a net vector that has components, or that has a magnitude, 8.7 squared plus 5.22 squared. And I raise that to the half power to take the square root. And I'd get a magnitude of f net of 10.14 newtons. If I wanted to find that angle, I'd do an inverse tangent. Nothing new is happening here, right? Taking the inverse tangent really quickly just to round it out, I'd have y over x, 5.22 divided by 8.7. That angle ends up being 30.96 degrees. Okay. What I want to focus on, though, is the x and y components. So I'm going to rewrite our net vector in vector notation, bracket notation, 8.7, 5.22 newtons. So this is the x and y component of our net vector. The reason I'm writing it like that is because if I were to need to do a calculation to find the acceleration using Newton's second law, I can express the acceleration as an x and y component just as easily because it's also a vector. In fact, our next question here is, okay, those are the two forces that represent two players hitting a hockey puck at the same moment, one with a force up and to the right, one with a force down and to the right, F1 and F2, F2 and F1 respectively, the way I described them. And if we know the mass of the hockey puck is 300 grams, what is the acceleration of the hockey puck at that instant when those forces are applied? Well, and this last statement here is saying those are the only two forces acting on it. We'll talk about friction starting next week probably. All this is asking us to do is to calculate the acceleration given the forces. By Newton's second law, the acceleration is F net over m, force over mass, the net force over the mass. The acceleration can be a vector in two components, so I can write 8.70, 5.22 as the x and y components for my net vector, divided by 0.3 kilograms. And now when I have this, remember the x and y components are treated independently. All I need to do is to divide both the x component and the y component by the mass, 0.3. That mass can be treated like a scalar multiple out front. When we introduced vectors, we said that I can take a vector and just adjust its size by multiplying by a scalar multiple. So this is no different than thinking of it as 1 over 0.3 kilograms times that vector of 8.70, 5.22 newtons. Newtons divided by kilograms is going to give me meters per second squared, which is an acceleration. All I'm going to do is take 8.7 and divide by 0.3 to get 29 in the x direction, and 5.22 divided by 0.3 to get 17.4 in the y direction. That's going to be my acceleration as a vector, as a two-component vector, depending on how I wish to express my answer. We can find the magnitude, we can find the angle. The vector formula, A is equal to F net over m, automatically tells me my angle because that formula tells me vector-wise, direction-wise, the acceleration must be in the same direction as the net force. All that mass can do is scale that acceleration larger or smaller than the net force vector in terms of magnitude. I'd like to work another problem where we can think about Newton's second law and what net force represents. Here we're going to limit our discussion to just one dimension. The previous example reminded us that everything we know about vectors can be applied to what we're talking about in terms of Newton's laws because it's a vector equation. We often will have a separation of x and y due just to the motion that we are going to consider, as well as a tactic that we're going to talk about starting next week that'll help us separate those two dimensions. So let's think about just in one dimension just to practice thinking about net force and how net force can be applied to Newton's second law to answer any kind of question that we have. So here we have a certain block. It has a weight of 1180 newtons, and it's hanging on a rope. We want to find the tension in the rope given these conditions. The thing we need to do here is to draw a force diagram so that we can determine what the tension is while reasoning about Newton's second law. So the first one says the block is stationary. Well, if we draw a force diagram for a stationary block, what do we need to be sure that our force diagram tells us? Well, if we think about stationary, the word stationary means that the velocity is zero, which means that my acceleration is constant at a value of zero so that my velocity is zero, right? I have an unchanging velocity. The velocity is constant, and therefore the acceleration is constant, and specifically the acceleration is zero. My constant velocity tells me that my acceleration must be zero, and now we can squeeze in Newton's second law that tells me that my net force must be zero because my mass certainly isn't zero. I have a 120 kilogram block. So my net force of zero tells me that my force diagram must look like the following. I have a downward weight. I have an upward force of tension. And so that my net force must be zero in order to give me an acceleration of zero, that tells me that the sum of forces, which is equal to the net force, just use that, whoops, I had a little bit of stutter there with my stylus. I just used that sigma notation to talk about the sum of the forces, all of the forces, which equal the net force. Well, that's just going to be the force of tension plus a negative force of gravity. And I know that my tension force and my force of gravity must sum together such that the net force is equal to 0. This tells me that my tension force is equal to my gravitation force, my weight, right? The weight of the object is equal to what we call F of G, the force of gravity. We introduced that in Wednesday's lecture. So I see I'm being very thorough and kind of overdoing it in terms of my analysis of this is equal to this is equal to this. But this kind of thinking is something that has to come somewhat second nature the more and more and more we work with these problems. If the acceleration is 0, let's follow the logical chain. If the acceleration is 0, then by Newton's second law, the net force must be 0. And now I can think about, well, what's the definition of the net force? It's the total vector sum of all the forces. Here I have two forces, one up and one down. They sum together to equal 0. That's what this statement says. Therefore, they must equal each other. They are equal and opposite to give me a net force of 0. This is not saying that the tension force is always equal to the weight and in an opposite direction, as we will see soon. I'm going to go to a new page, so let's just take a moment to make sure we can think about what B is asking before we draw it again. Now the block is moving upward at a steady speed of 5 meters per second. So I have the same block. Here's that block. It's has a rope attached to it, right? And it has its own mass, right? Because it's a 120 kilogram block. Now I'm not drawing a force diagram, I'm drawing just a cartoon of the scenario. And now we have upward velocity of 5 meters per second. But we say we have a steady speed. That tells me something about the acceleration. Even though it's moving, the acceleration is equal to 0. So all of our logic from the previous example falls into place here. This acceleration is equal to F net over the mass. So the net force must be equal to 0. That's the sum of all forces, which means I'm going to have an upward tension force and a downward gravitation force. Here's my force diagram. It looks exactly the same. An upward tension force, a downward gravitation force. Since they sum together to equal 0, even though the block is moving, Newton's laws tells me that in this case, the tension force is equal to the weight yet again. Now, the last example was a bit interesting. Now it's accelerating upwards at 5 meters per second per second. So the block is going faster and faster and faster. Let's draw a force diagram for this one. Here we have, let's draw a cartoon first, right? Same rope, same everything, but now, I have an acceleration going up. Awesome. My acceleration must be equal to my net force over my mass, and my acceleration is equal to 5 meters per second squared. So what does this tell me must be true about my forces? Well, at this point, I'm going to rearrange this equation and say my net force must equal mass times acceleration. And then the net force for this diagram, I'm going to have an upward tension force and a downward weight force. Oops. Let's make that look a little nicer. A downward weight force. Here, I've exaggerated the fact that the tension is larger than the gravitational force. Why is it larger? It has to be larger because we see my acceleration as a positive value. Here I have implicitly chosen up to be the positive. I'm calling it the y direction. I could call it the x direction if I wanted to. But up is the positive direction. So I have an upward force that must win. What's my net force? It's the sum of all my forces. So here I would have, again, Ft plus the opposite of Fg, because it's pointing down, equals mass times acceleration. my goal was to find the tension force. So here I have that the tension force is equal to mass times acceleration plus the force of gravity. So I have 5 times 120 kilograms plus 11, what was the weight? We'll talk in just a moment about 1180. Come on now. Plus 1180 newtons gives me my total force of 1780. Whoops. I'll put the N below it because I see him right under my picture there on the bottom of the screen. So I needed to pull upward with a tension force larger than the weight in order to accelerate this object upward, because I needed to give it a non-zero net force in order to have an acceleration, which is what Newton's second law says. Let's remind ourselves for a moment, while we've talked about weight in this problem, about what weight really is. Weight is a force that is due to the gravitational interaction between a mass of an object and the mass of the Earth. We'll talk in more detail in a few chapters about weight as a fundamental force using Newton's universal law of gravitation. But right now we can use Newton's second law to understand weight a little bit if we think about a case of an object in free fall. We remember we defined free fall as an object that is only acting due to gravity pointing straight down. Well, now we know that gravity is a force. So in free fall, the net force is equal to the force of gravity, and that's equal to mass times acceleration by Newton's second law. So our weight is equal to mass times a specific acceleration. We know the value of that acceleration is g. Note here, I haven't defined the direction to be negative. Typically, when we are talking about weight, we just want to know what the weight is, and depending on the context of the problem, we will assign a direction for weight, typically down, typically negative, but doesn't have to be. So again, as I've made the case earlier in the class, G, you can tell just by the tone of my voice, I'm already annoyed just having to say this, but it's important. G is not negative 9.8. G is 9.8. The direction is our choice, which way we want down to be, positive or negative. That's where, problem by problem, we will assign a direction for the gravitational force. And then when we sum the forces, it'll have a plus or a minus sign, okay? When we just say an object's weight is equal to m times g, then we haven't installed a negative sign because we don't know which way we chose our coordinate system to be. The little rhyme that's sometimes useful is if you have the mass and you want the weight, you multiply by 9.8. G is equal to 9.8, right? So mass times 9.8 gives us the weight of an object. I will always write F of g for the force of gravity, but that is representative of the weight of the object. So just a little aside about objects in free fall and relating weight to mass. We ended class on Wednesday describing Newton's third law, and that the idea of Newton's third law is that forces arise in pairs, these action-reaction pairs. And I want to work through an example or two and then talk about weight and the normal force as our first specific force, special force that we need to consider in order to work more and more complex problems. The key to Newton's third law is that the forces arise in pairs and they act on different objects. They are equal and opposite in direction, so the force of the hammer on the nail is the same as the force of the nail on the hammer, but the key here is that one of them is the hammer pushing on the nail, the other is the nail pushing on the hammer. They are acting on different objects. Those forces are equal, but because they act on different objects, it allows us to see how that object is changing its motion in response to an interaction it has with a different object. Excuse me. So here we have a skater pushing off of a wall. Now, of course, the skater pushes on the wall in order to move backwards, but it's not the skater's push that makes her move. It's the wall pushing on the skater that makes her move. If the skater pushed and the wall wasn't there, of course they wouldn't move. So the wall had to be exerting a force on the skater in order to make the skater move. Again, it seems a little counterintuitive because we know that the skater doesn't move unless they push on the wall, but we also can't talk about the skater moving unless a force acts on the skater, and the skater cannot act on, in this case, herself. In the diagram, the wall had to be pushing on her. So we do have to be careful about how we talk about which object is doing the pushing, especially as we get into more complex problems that have multiple parts in them. Are we talking about object A on object B or vice versa, etc.? We also have to be careful not to include both of the third law pairs on a single object. For instance, when we walk, we push on the ground and the ground pushes back on us. If we included both of those in our force diagram, Newton's third law says they're equal and opposite, so they will cancel out if we treated both of them as forces on our object. That's not true. One of them is us pushing on the ground. The other is the ground pushing on us. So if we're talking about our motion, only that second force is included in the analysis. The other is us pushing on a different object. We would worry about that object in order to do an analysis of that object's motion. So we can't include both of the third law pairs on a force diagram because only one of them is acting on the object of interest. Again, the third law is really just a rule that we use in order to make sure we're talking about the correct forces. Here's a diagram that, again, reminds us that not only are the forces acting on different objects, but they're equal and opposite in direction, and that helps us to solve different kinds of problems depending on the question that's being asked. Let's work a problem very similar to these diagrams here, where we have an object being pushed to the side, and we want to know the acceleration of the blocks and the force that A pushes on B or that B pushes on A. Now, I'm going to solve this problem in the first part in two different ways that may be counterintuitive depending on how much we've worked with something like Newton's third law in the past. Let me find my notes for this problem to make sure I don't make a boo-boo math mistake while I'm working it. So one way to think of this problem is to imagine that the blocks are just acting as one block. If we just say, okay, here we have, whoops, wrong pen. Here we have a block that is together A and B, of which we know the total mass is 5 kilograms. Let's see what Newton's laws can get us to answer these questions. So if we say, okay, we know we have a pushing force. Here's our diagram. We have a pushing force. We weren't told anything about friction. We're going to get into friction next week. So that pushing force is the only force of note acting on our object. There is the force of contact from the table going up and the force of the weight going down. We'll see next week why we can ignore those. Right now, trust me, we can ignore those. I only care about the forces in the horizontal direction. So Newton's laws say that the acceleration is equal to F net over the mass. F net in this case is just the pushing force over the mass, and I have a 10 Newton pushing force over a mass of 5 kilograms. So I have an acceleration of 2 meters per second per second. Great. Awesome. That was question A. We nailed it. Now, question B, with what force does A push on B or B push on A? Our analysis of this object as one single thing getting pushed to the side doesn't tell us anything about that interaction between the blocks of one pushing on another. In order to answer a question about how does one block push on the other, I need to treat the blocks separately. The great thing that we'll start to see, especially next week as we do more and more complex problems, we don't need a new strategy or a new formula. We are going to do the same thing. We'll just do it again once for each block. Here's what I mean by that. Now we're going to consider the blocks separately, block A and block B. Block A has the hand pushing on it. Block B does not. A has two forces in the horizontal direction then. A has the force of the push, so this is a free body diagram for A, has the force of the push, but it also has a contact force of B acting on A. So we'll draw F, B on A. Block B has just one force acting on it, F, A on B. And these two forces are third law pairs. I like to highlight or circle my third law pairs in two separate diagrams so I can keep track of which one's which, or rather, which two forces must be equal and opposite given the rules of what a third law pair is. Notice how the force diagram for B doesn't have any information about the push on it because the hand that's pushing is not touching B. This is one of the things we talked about on Wednesday when we introduced forces and how we name our forces or identify our forces. The hand is not touching block B. Block A is touching block B. So that's the only thing that's allowing B to accelerate. The blocks are together, so the accelerations are the same. Let's write Newton's second law in the following way. I'm going to write that my net force is equal to mass times acceleration. This is a more useful way, I think, of doing it because I'm going to solve for the acceleration. It doesn't start with acceleration equals, but allows us to think about the forces separately without having to worry about dividing something into all of those forces. Now for A, my net force is going to be the sum of F push plus B on A is in the negative direction, so I'm going to have minus B on A, just like that. And that's going to equal the mass of block A times the acceleration of block A. So I'm going to just make this a little neater. I see it's a little sloppy. Here we go. F push plus opposite of FB on A equals mass times acceleration. Now, for block B, my net force is going to equal mass times acceleration. Well, the net force is just F of A on B, and that's got to equal the mass of block B times the acceleration. Now here, our accelerations are the same, so I do not have a subscript on one A or the other. The blocks stay together, and therefore the acceleration of A is the same as the acceleration of B. That does allow me to do a little bit of algebra solving because I have two equations. These equations here. And right now, I have three unknowns, right? I have B on A on B, and the acceleration A. I have two equations and two unknowns, so I need a third equation. Well, the third equation comes from Newton's third law, which is that the magnitude of FA on B is equal to the magnitude of FB on A. The opposite nature is already in our equation. This one has a negative sign in front of it because it's pointed to the left. This one has no negative sign on it. It's positive because it's pointed to the right. So therefore, this third equation here allows me to make some substitutions to get just two equations and two unknowns. Here's what that looks like. Let's see. I'll go to my next page. So we have, we don't want a highlighter. We want that red pen back. F push plus minus FB on A equals mass of block A times A. And then I also have that FA on B is equal to mass of block B times A, using the fact that FAB and FBA have the same magnitude from Newton's third law, I can substitute this in here because AB is equal to BA, and that gives us F push plus minus mass of block B times A equals mass of A times A. Now I can just solve for F push equals mass of block A plus mass of block B. Here I'm doing two steps in one. I added it and then I pulled A out. Notice how this relationship to get the acceleration is no different than this relationship here with a little bit of algebra rearrangement, right? This is how I would solve for A. I would solve for A here by saying that the acceleration is the force of my push over the mass of block A plus the mass of block B. So that's a 10 Newton force over 1 kilogram plus 4 kilograms. Well, that's 5. 10 over 5. I get the same answer. Well, that's good. I shouldn't expect to get a different answer just by considering the problem differently. Now, here's where this type of analysis is going to come into play. I can answer that second question of what's the force of B on A or A on B because I have a relationship right here that allows me to solve for one of those, right? Using this acceleration, I can take that acceleration and find the force of A on B, would just be the mass of block B, 4 kilograms, times my acceleration, 2 meters per second squared, gives me 8 newtons. And I can look back and make sure that I can substitute that 8 newtons in for the force of B on A by the third law. That must equal the force of B on A as well. I can substitute that into this equation, and it works out just the same. So a little bit of a different analysis allowed us to see that I could now solve for an additional piece of information, that being the force of one block on the other. One thing that we need to be a little careful about when we talk about the normal force, this will be the first force that we introduce in terms of an additional force that allows us to solve more complex problems. If an object is resting at something like a table, on something like a table, there is a force of contact of the table pushing up into that object, and it is an error that's sometimes made that the gravitational force and the normal force are a third law pair. They are not. If we look at this bust of Abraham Lincoln, it has a downward weight, and it has the normal force acting up on it from the table pushing up and supporting the bust. But they are not a third law pair because one of them is due to the earth pulling down on the object. That's the force of gravity, right? This agent is the earth. This agent is the table. So they are two different agents acting on the same object. If we look at this diagram here, the second diagram, let me move me up to this different corner here. So if we look at this diagram on the right, now we see that I've got Fn and Fn prime. That's the third law pair. One is the table pushing on the bust of Abraham Lincoln. The other is the bust of Abraham Lincoln pushing on the table. You see how those objects and agents are reversed. So when we think about the normal force, is it related to the weight? Sometimes. It is not always equal to the weight, as we're going to see in just a moment. For this case, it is, just like that previous problem of the block with the rope and the weight. Those are the only two forces, and the object of interest is at rest. Of course, those are equal and opposite, but that's not always the case. If we think of something like a person in an elevator, here this elevator is accelerating upwards. If we were to have a scale right here that would determine the weight of the person, and I think about the need for the person to accelerate upwards, well, this downward weight, here in this diagram, they use a W for the weight, has a certain value, right? We know that the weight is equal to mass times the acceleration of gravity. That's the magnitude of the weight. the net force must be upward while the person accelerates upward, which means that the force of the spring scale, that's what SP represents, the bathroom scale under their feet, must be larger than the weight in order to accelerate them upwards. So because, again, we've identified that we know they are accelerating upwards, we know that, therefore, the net force is upwards by Newton's second law, that tells us that the force of the bathroom spring scale on their feet must be larger than their downward weight. This is what's called apparent weight. This apparent weight is the normal force of the thing underneath your feet that's pushing on you. Under normal circumstances, and maybe I should say the usual circumstances, I don't want to use the word normal to mean usual and perpendicular contact force, both, that'll be confusing. So the usual circumstances are that you are not accelerating up or down. You're standing on a motionless object, and you therefore are motionless and not accelerating. So under those circumstances, your weight and your normal force are the same. The feeling that we have of the floor underneath us is our own perception of our weight. When that floor pushes on us or is pulled away from us, we feel our weight differently because it's not what we're used to experiencing. That's the apparent weight. So here in this example, we'll end with this. I'm going to stop talking. Whoops, I need to move me. There we go. I'm going to stop talking in just a minute because I want you to start working on this and to show me your work for in-class credit today for watching the video. We will pick up with this on Monday. So your in-class credit doesn't necessarily have to be a correct solution. I want to get to a point where we have a force diagram and we can maybe think about what the force diagram looks like in order for us to take the next steps to answer this question. So your goal is to give me the force diagram for this problem. And I also want the direction of the net force to be clear on your diagram, just like the previous diagram had. So read this problem carefully, come up with a force diagram, pay careful attention to the size and direction of your arrows, and think about the forces that are acting on this person in order for them to experience a net force, and then we will think about answering the second question starting class on Monday. So judging by my timer, we have a 42-minute video. This gives us official time in class, if you're watching the video, 8 minutes or so. So go ahead and work on this. I will make sure that there's a place in Blackboard for you to submit your diagram. We will pick up with this diagram to answer the question on Monday. Thank you for the hard work, everyone.